work with my colleagues Mr. Campos and Juan Huete, and the title is Fusion Strategies to Combine Topical and Temporal Information for Publication Venue Recommendation. So, well, basically, the problem that we are facing is where to publish my last paper. What is the best appropriate journal or conference to submit this new piece of research? And then, well, I think any of us has got our own criteria, we could say, you know? But some of them are the suitability of the article topics with those treated by the tentative publication venue. For example, the impact factor or any other criteria. We are going to focus on content. Basically, we are trying to match the content of our paper with the content of the possible journals. So this problem can be addressed using a recommender system with the two basic alternatives that we've got, collaborative filtering and content-based recommendation. We are going to work in content-based recommendation. So what is the context? Well, we are going to represent journals using profiles. Profiles in any or other way, as we will see later. But basically, these profiles contain content which is based on the content of the articles that have been previously published in these journals. We have worked on this, and we have developed several models to deal with this problem. We have designed several types of profiles, which, well, we haven't designed. Some of them are state-of-the-art. And you can see here, for example, the first simple representation of these profiles is just consider each paper a single profile of a journal itself. So we could say that a journal is composed of lots of sub-profiles representing each published paper. With the second alternative is what we call the monolithic profiles. It's just a compendium of all papers published in the same journal. So we've got one profile per journal. And then the third approach, this is a contribution, is, well, we are going to create several subprofiles per journal. And how are going to be organized these subprofiles? Just each subprofile will deal with a topic of the journal. So in order to create these subprofiles, we are going to perform a clustering process. We are going to find the different topics in the whole collection of documents, whole collection of articles, and then we are going to create subprofiles for each journal, taking into account the topics that each journal deals with. Okay? Perfect. In this paper, what we are going to do is just to think about the incorporation of time and topics, as we will see later, and how we are going to combine them. But, well, this is a case, a very common case. For example, I'm going to read it. If venues A and B both have published articles related with the main topic of the target article, but in A, we can find more recent articles than in B, then probably we would prefer to publish in A because they've got more recent articles. Okay? Well, we are going to address these two research questions: how temporal and topical information can be used alone to solve this problem, how we can combine, and if it is worth to combine them. So, well, this is a image dealing with how we are going to create the monolithic profile and the atomic profiles, as I explained before. And then we've got an alternative, which is create topical orthomagic subprofiles. We could use clustering as we did in previous research, and we also can use LDA as we are going to do in this research. It's basic topic modeling algorithm. So as you probably know, LDA tries to find latent topics in document collection, and each latent topic is characterized by a probability distribution of terms given. But in addition, we've got another probability distribution, which is for each document the probability distribution of topics obtained all the topics obtained for each documents. So we require a parameter k, which is the number of topics. And well, what we are going to do is just to use LDA to create subprofiles of journals. How are we going to do that? Well, we are going to run LDA, and then we are going to get these two distributions, probability distributions, and then for each article A, we are going to associate each article to the most probable topic. Okay, and then for each journal and for each topic in which there are articles in this topic from this journal, this is a little bit we are going to create a subprofile joining the article. So imagine that a journal deals with 5 topics. Then we are going to have 5 subprofiles, and we are going to include in each subprofile all the articles dealing with each one of these 5 topics. Okay. Okay. So this is how we are going to create the, should be a point anyway, but I don't find it. Okay. So we've got LDA, the different clusters, and then we are going to create the topical profiles. So how are we going to recommend? Well, we are going to use a content-based approach in which the query is going to be the article to be submitted. It's composed of all the subprofiles that we've got from all the journals, different journals, and then we are going to get a ranking of subprofiles. We should get a ranking of journals. We will explain later how we are going to transform this ranking of subprofiles to journals. And how are we going to manage temporal information? Well, this is a very classic way of managing information, temporal information in information retrieval and recommender systems, which is to use a temporal decay function. It's just that we are going to consider the difference between the publication year and the current year. Okay, so our recommender system based on temporal information is based on these steps. We've got an index of the atomic collection, the single articles, and then we are going to obtain a score for each article. Then we'll compute a modified score based on the decay function. And then we've got a ranking of articles. Again, as we are going to recommend journals, we have to transform this ranking of articles to a ranking of journals, as we will explain later. So, this is how we are going to do this conversion. We've got a ranking of articles or a ranking of subprofiles, depending on working on temporal or topical recommender system, and then we are going to use this this method to get basically. It is like if we score for each journal, we sum all the scores of different articles related to all the different subprofiles related to this journal. And how are we going to do? It's basically sum up the scores of all the sub-profiles articles associated with each venue, but taking into account their position in the ranking. So basically, is that using a logarithm evaluation. And finally, we are going to get a score of journals. And how are we going to combine them? Because our assumption is that if we got a temporal recommender system and a topical recommender system, well, not to combine them in order to try to improve the performance of the recommendation. So basically, we are going to apply, and this is the core of the paper, different combination of fusion of aggregation strategies based on the score and based on ranks. Based on score, just combining scores from rankings. Based on rank is just using the some information given by the ranking, but not the scores themselves. Okay, these are the two types of fusion strategies. So score-based methods are, for example, the combination, the sum of the scores. The first one, on sum, which is just summing the different scores, the score given by the temporal recommender system and the score given by the topical recommender system. And then we've got another approach which is similar, but tries to promote those values appearing in more frequently in the ranking. So we multiply 2 times the sum of the scores if the journal appears in both rankings. And we use the ranking in any of them is only if only it appears in one ranking. And then a linear combination, basically linear combination. And then we've got the rank-based methods. We've got 2 families of methods that we have evaluated. It is board account. It's basically transforming the rankings into scores, which are combined in different ways, as for example, Borda sum or Borda prot or Borda L2, which basically works with the position in the ranking, not with the score itself. Okay, with the position. And then, well, we have used Condorcet. Well, basically comparing pairwise, doing pairwise comparison. I'm not going to explain the algorithm because I am out of time. And then we have used a collection based on biomedical journal papers with these numbers. We have used title, abstract, and keywords and publication year. And the training is composed of year 2007 to 2015 and test article from 2016. We have used LDA, stop word removal, stemming. We have done some term selection, and we have used this number of K because it's the number of descriptions in the second level of the mesh thesaurus. We have used these 2 types of decay functions. We have employed LASIN as an information retrieval model or system inside. And these measures, and well, these are the results, and basically there are no the differences between the different models combining time and topical topics are not very large. Independently on the measure that we have used, the tendencies are basically the same. All the fusion strategies improves the temporal and topical systems isolatedly, and we have seen how combining these 2 types of information, the results are better than using them isolatedly. Well, this is more or less how the different types of combination. The is the best one. It's better than the topical isolated, the temporal isolated, the atomic and chromatic. So it's worth to combine information. And well, basically, what we have done is just to design two different type of recommender system based on time and topics, and then we have combined and we have shown that the combination is good. So this opened different new research lines about trying to investigate more deeper models about how this combination can be. So maybe we can use what we call topical temporal subprofiles, which is subdivide topical subprofiles into a period of times, or it's basically create different periods of time and then learn an LDA inside period, or the other way around. Okay, that's all. Thank you.
So, is there any question? No. So I have a question about the ground truth that we used. So you assume that from historical data, like if something is published in a journal, you assume that that is the reference truth, that is a ground truth. Right? Now it may turn out that the authors didn't have the system, and they didn't know that if that was the appropriate journal to publish their papers. So can you see a cycle there that maybe you are it's maybe there is something wrong in assuming that just because of the fact that something is published in a venue, it means that that is actually relevant publication for that paper.
Yeah, you're right. But well, as soon as they have our system, they will change that. So yeah, you're right.
Yes, but when you are evaluating the systems, you're still using that data, which means that there could be a bias in your evaluations as well.
Yeah, but it's supposed that this data will be, that we could say that the temporal window will be moving. So in that case, that might be important for that.
I have a curiosity more than a question. So basically, you are using the terms, the keywords from the research papers, which are manually annotated, in order to produce a content-based recommendation. Did you study how bad is there the effect of the code keyword? So let's say that to write a paper, they use a keyword which is not in the system before. Like I don't know, at some point, transformers was a keyword probably in one paper and it was not there before. So how many cases you have where papers? It should be interesting because it's any kind of code situation in the system. Because, okay.
And this is a clue of a new topic coming to the research context. So it's true.
Now, Ahara is going to present his work on tag-based embedding representation on neural-relative filtering recommendation. He's from EB, right?
Okay, thank you.
Speak here. We'll have to mute.
Okay, so we're going to discuss our paper entitled Tag-based embedding representation in remote collaborative filtering approaches. Okay, so let's begin first by outlining our plan. After introducing tag-aware recommender systems, we details classical tag recommender system and give in contrast how neural models for recommendation can improve particularly rating prediction task. After that, we introduce our proposal models that do integrate static and contextual tag embedding representations. Then, thanks to different neural collaborative filtering architectures, we are going to discuss our results and we will draw our conclusion and give some perspectives. Okay. So, in collaborative systems, there are several contents surrounding users and items. For an example, in YouTube platform, they integrate such contents in the form of keywords or tags. Since such way of indexing and classifying was very popular in the Web 2.0, they are commonly recognized as relevant information to be leveraged with collaborative filtering approaches. So, in some sense, for recommendation tasks, in particularly for rating prediction, starting from two matrices that are the item tag and the user tag matrices, classical approaches for the most use or exploit simple user item similarity methods or matrix factorization techniques like SVD. In some sense, those classical approaches from user tag property, those classical approaches exploit and combine from user tag properties different dimensions and use them as features. Particularly, these models share the property of being linear, since they combine user and item latent factors linearly. In contrast, tag-aware deep learning models for recommendation have the main property of of learning multiple level of representation, and hence have enabled the deep integration of different several type of contents. As a result, recent neural collaborative filtering approaches capture more complex user item interaction, has enabled high-level abstractions for content applications. Particularly, we have presented some works of the literature. In Zhu and Hou, for example, they take the tag-based user and item profiles as inputs of two deep neural networks with shared parameters. Input are then passed through multiple hidden layers and projected into an abstract deep feature space on the final hidden layer, where the similarities between the abstract representations of user and item profiles are computed. Then, finally, a recommendation function is used to rank by applying a simple softmax function. In the work of Zhu and Hou, we can notice that they propose on their work, user profiles are initially represented by tags, and then a deep neural network model is used to extract deep level features from tag space and then layer by layer. Such a model learns features using a sparse autoencoder. Based on those extracted features, user profiles are updated based on the user tag matrix that is used to build similar users. In the work of Liang and Hou, they propose a deep learning model to improve the performance of tag-aware recommended system by using a pre-trained word to vec. They averaged the tag embedding representation of user and items, and they use in parallel a recurrent neural network, and they extract the latent features of users and items and put them into comparison to generate recommendation. Our proposed models were created by analyzing some end-to-end neural collaborative filtering architectures that were based on the user rating space exclusively. So, particularly, our models have integrated tag-based embedding from pre-trained, static, and contextual, but in different ways. So, the first model, the first of them, use as input multiplication of user and item tag-based embedding vectors, and then rating prediction is granted thanks to simple MLP. The second exploit in input LMOI's multiplication of user and item tag-based embedding vector, and then vectors are concatenated with user rating vectors in a multi-encoder architecture. The third model approached the problem of rating prediction by formalizing it through a bipartite graph. First, the neighborhood function is fixed size, and the bipartite graph is sampled as the model learning function that generates aggregates from tag-based textual feature node neighborhoods. This method can be generalized by applying different aggregation methods to nodes. We have exploited two of those methods. The first one is a mean aggregator function, and the second one is a convolutional aggregator function. The mean aggregator function does average tag embedding features from the neighborhood of the node, and the convolutional aggregator function concatenates nodes from the previous layer representation. So, for static tag-based embeddings, we have already in our experiments word-to-vec representation of tags per user. And concerning contextual tag-based embedding representation, we have extracted them from BERT, and we have assumed that the first token, which is the CLS class, captures the context and is treated as sentence embeddings. So, for our experiment, we have oversampled minority classes, since you can notice in the graph that user ratings are unbalanced. So what we did is that we oversample minority classes by duplicating samples from the minority class and then adding them to the training data. After splitting the data in each dataset in random 19 and 10% training set and testing set, we hold 10% of the training set for hyperparameter training. We found that some tags were out of vocabulary, since those user tags represent respectively 8, 5, and 5% for all the moving datasets distributed between tens million and 20 and 25 millions of ratings that compose our dataset, our movements dataset. We fixed this issue simply by samples with random vector values corresponding to the dimension of the tag embedding. Okay. We have conducted a 10 cross fault validation strategy in each dataset, and I rated both root mean square error and mean absolute error measure. Moreover, we have also evaluated ranking accuracy using the normalized discount cumulative gain at 10. Results suggest that neural graph collaborative filtering approaches describe strong performance considering the significant improvement of the neural models that do integrate contextualized tag embeddings. We also found that mean aggregative function, which is operated with static tag embeddings in neural graph collaborative filtering, has also performed well. However, we found also that impact of contextualized tag embeddings on models is definitely proven, since both RMSE and NIA scores have shown significant improvements. We also provide on our paper for each neural models error distribution, since the paper discusses the effectiveness of our approaches on predicting user ratings with an acceptable amount of error. The paper also discussed and gave models validation score after 20 epochs. And here we can draw our conclusion by saying that neural graph models to learn aggregation functions has enabled us to gain quality recommendations. Another way, we have shown that handling a convolutional aggregator function can generalize an efficient graph-based neural collaborative process. This has enabled us to gain more refined embedding features and then to achieve and to catch non-trivial tagging behavior. As perspectives, we can say that there are other ways to extract tag-based contextual embeddings from BERT. Another point is that determining ideal tag-based neighborhood or neighbor embedding representations is time-consuming. So we realized the experiment with K. K is the neighborhood layer. So in this case, when K equal 2, the embeddings will go through 2 layers of representation on the neighborhood. So we can also dig and explore tag-based contextual embedding by representing in a recurrent neural network, and this granted into a neural collaborative filtering architecture. Thank you.
I have a question about this metric that you use for evaluation. You use the root mean squared.
Yes.
Now, what is the ground truth value that you consider? So this is a ranking task, right? This is not.
It's not a ranking task. It's about predicting user ratings. So the ground truth is the true user ratings that we have used and trained before. So it's what we have done is that we moreover we have integrated another measure that is NDCG. It's for ranking, and that we evaluated for NDCG at 10. So this is quite different.
So what were these varying values like? I mean, your audience scores are something like 0.7 in that range.
Yes.
Now,
This is, I think, this is because of, when you say contextual embedding, you are necessarily to fine-tune a BERT model, but there are also, for example, in our experiment, we only took the vectors from CLS class, so it generates us embedding. contextual embeddings. But there are a lot of work that suggests that those embeddings can be extracted from other layers from the model. For example, the before last hidden layers, or the fourth the fourth layers of the model. So there is still experiments to do and to establish which exactly which tag ending, which contextual tag ending to use in such kind of task. Yes. Yes.
How frequent is that?
Yes. Yes. As I mentioned before, there are, as you said, tags or words that are out of vocabulary that happen in word-to-vec approaches, in word-to-vec model. Since word-to-vec is a kind of neural language model, so we have simply replaced those vectors by random vectors values in tag space, in word-to-vec tag space dimensions. Why we did that? Since those tags didn't represent, do not represent, they are not many. They just represent 5% from the data set. So that's this one.
Is going to present this work with about saying use a recommendation with knowledge graph.
Hello, I'm Oliver. I'm a PhD student at the University of Freiburg in Germany, and I would like to present our work on a recommender system that can foster serendipitous discovery. Now, let's talk about serendipity first. Imagine you listen to music online and you exclusively to the Beatles. Based on this information, a recommender system may recommend you some of John Lennon's solo work, but it's unlikely that it would recommend you a heavy metal band. Now, assume that you're at a cafe and listening to the radio, and they're playing a song by Iron Maiden. And you're really surprised because it turns out you love this band, and you discover perhaps the entire genre of heavy metal music for yourself. And we call such a happy accident a serendipitous discovery. And more generally, it can be thought of as the art of making an unsolved finding. We discover something new, unexpected, but relevant. Why does serendipity matter in the context of recommender systems? Well, for one thing, it has the potential of expanding your users' interests, and they gradually get to improve their vocabulary of your domain. So they learn new things, which in the end may lead to increased user satisfaction and increased engagement with your platform. On the other hand, serendipity also has of increasing catalog coverage because users get exposed to more items in your database, and especially items that may appear in the long tail of popularity as opposed to probably popular items. So with these ideas in mind, we constructed a simple knowledge graph on the domain of music consisting of tracks and genres. And we use several publicly available datasets to build this model. And the tracks are taken from a dataset containing listening events of users on Last.fm. So we actually know which tracks users listen to. And we enrich this model with contextual information available on tracks in the form of acoustic features. These acoustic features basically describe what a song sounds like or feels like when you listen to it. Our network contains about 250,000 nodes, connected by 1.1 million edges. And yeah, with this model in place, we designed two scoring functions that we apply to tracks. And the higher the score for a track is, likely it's that we recommend it to user. We evaluate the effect of each of the scoring functions separately, so we have one model per scoring function. And the scoring function on the left here is both of these scoring functions take into account the track's popularity on a global level, as well as the similarity to a user's listening profile. The function on the left simply discounts similarity to the profile by popularity. So simply said, a track that is less popular receives a higher score than a popular track. And the scoring function on the right, in addition to discounting by popularity, it also boosts the similarity to a listening profile. So as you can see with the middle and bottom curves here, the green and the blue curves, a track with a low similarity of 0.1 to a listening profile receives a higher track than receives a higher score than a track with a similarity of 0.9. So what do we apply these functions to? Which tracks do we apply them to? Remember that I said earlier, serendipitous discovery was about something new, unexpected, and relevant. Our scoring functions already ensure a certain level of unexpectedness, but how do we ensure that what we recommend is also new and relevant? Now let's assume that this simple network here models the user's listening history. The colored circles are the tracks the user listens to, and their associated genres are the empty squares. This is a bipartite graph, which means that we can take the one-mode projection onto the genre vertices. And we arrive at what we can call the user's genre history. Now, we borrow a concept from social network analysis called reciprocity, which is the idea that if three nodes in a network are connected in a triangle like this, there is some form of strong mutual relationship among these nodes. If you think of the nodes as people, this is the idea that a friend of a friend is also my friend. When we apply this to musical genres, we can say that if we know that the user listens to two genres that have a mutual neighbor the user is unaware of, this is the colored square in the top right here, and by listening to this genre, the user can go deeper into the overall genre graph, but maintain a strong connection to what they are used to their previous experience. So because we need tracks, essentially what we do is we take all tracks that are assigned to two genres the user has listened to, and keep only those that we know the user has not listened to, because we have this listening history available. And the idea is that by listening to one of these tracks from the intersection of two genres, the user may be exposed to a genre that they haven't heard of yet, and can make a serendipitous discovery. So with this model in place, the question inevitably arises: how do we evaluate such a model? Recommender systems are typically evaluated with measures such as precision or recall, or in more general terms, measures that determine to which extent a known ground truth was recovered. But we are dealing with an element of surprise here. So how do we know what the ground truth is supposed to be? What we decided to do instead was to measure the quality of the recommendations that we return in terms of novelty and diversity. And we turned to existing literature to find measures that approach these two notions. Novelty is the idea of captures the concept how new an item appears to the user, and diversity measures how different items are among each other with respect to some defined criteria. We approach novelty through a measure known as unexpectedness, which is basically the average distance of the recommended of the items in the recommendation set to the items in the historical set of the user. And this is parameterized on the distance function here, which really can be any distance measure that's suitable. We use cosine distance because we're dealing with vectors of acoustic features. For diversity, we decided to measure it on a content level as well as on a structural level. And for the content level, we adopted a measure known as intra-list diversity, which is simply the average distance among all items in the recommendation set. And the same remarks apply to the distance measured in here. It can be anything that's suitable. For structural diversity, we decided to measure the topology of the network that results when we construct a network of recommended tracks and their associated genres. And we use a measure known as the degree Gini complement, which is a measure based on the Gini index and therefore is a measure of disparity, in this case of degree disparity in the network. So it tells us how evenly is degree, node degree, distributed, what has skewed is it? Is the distribution dominated by a set of very central nodes or very high degree nodes, or is it even? And before you try to parse this lengthy formula, let me illustrate with a simple example. The star-shaped graph on the left here would have a degree Gini complement of 0.7, whereas the ring on the right here has a maximum degree Gini complement of 1. And as we can see, the degree in the graph on the right is completely evenly distributed, whereas on the left, the distribution is dominated by this very central node. So we applied all of these measures to our two models. We have one model per scoring function, and we compared our results to three baselines that are more traditional approaches to recommender systems. And let's start at the left here. For diversity, inter-list diversity, we actually saw that the baselines outperformed our models, which means that we do not return overall diverse recommendations, which we attribute to the fact that we try to maintain this strong connection on two genres, and perhaps it's the case that this doesn't lead to tracks that are overly different because they share two genres. And if you think about your own listening preferences, the genre tends to be quite similar across different artists and tracks. For the notion of structural diversity that we employed, we saw that the scoring function that boosts dissimilarity results in a higher degree Gini complement, which means that the networks that are returned by this model are somehow more homogeneous. They are more evenly connected than our baselines. And finally, for the measure of unexpectedness, we again see that the model with the dissimilarity boosting scoring functions outperforms the baselines, which we simply attribute to the fact that these scoring functions are designed such that they favor unpopular and dissimilar content. So I showed you how we can employ a simple knowledge graph together with some scoring functions to arrive at a model that may foster serendipitous discovery. And what we plan to do in the future on this is perhaps extend this knowledge graph with further classes. For example, it may be interesting to introduce the artist into this model, because that would allow us to filter out tracks by artists the user is already familiar with, and this increases the chance then of a more surprising recommendation. We would also like to extend this model to other collections than simply musical tracks, for example, digital archives or digital museums. And finally, what we really need is a user study, because again, it's only the user that can decide if what they receive from a recommender system is Thank you. That's it. I'll be happy to take your questions.
Thanks for all the good talk. So I'm just wondering, so this is a supervised approach that you have, right? It's not supervised. So I'm thinking that can we use these functions that we have talked about, these discount functions and the heuristic one? Is it possible to use that to also create a supervised model? So what I guess is like, if you take that as contextual information, so for one item that's significantly different from the other ones in the previous context that the user has seen, and if the rating is quite high for the item, so maybe that's an indication that that's an item that's limited features and that's very good as well. So is it possible to use these kind of signals to train a neural model?
Excellent remark, thank you. I believe it is. I think the big problem that we're facing is that we lack the data to confirm this, yeah? Because serendipity isn't something that's currently part of the business model of most of these content providers. So it's very rare, and so exactly as I outlined in the example, you would be in an offline setting at a friend's place like a cafe, if we stick with the music example, and you're then exposed to something new. Or I don't know, I would say similar things apply to books. Yeah, if you have, yeah, I won't stress the examples. I can't come up with an example now, but I believe it's true. However, we need to be on the lookout for these serendipitous discoveries and maybe find ways to measure when a user does make one of these discoveries online. Thanks.
I will ask you something. So one of the things that you decided to leave on the observation was these class belonging to different gender. So how big is the overlap? So on average, how many genders do we have in the collection per?
That's a good question. I don't have these figures in my head at the moment now. What you can see here is, maybe this answers your question to a certain degree already. The average degree of a genre node is around 540, which means that on average the genre is assigned to 540 tracks, with a huge spread in the data. And on average, a track is assigned 5 genres plus minus 4. Is that?
Yeah, I mean,
Yeah.
and then, if I understood correctly, when you figure out the team, you're evaluating on track level or gender level?
No, on the bipartite level. So we recommend the tracks to the user, and when we take these tracks and put a larger model, we infer the connections between genres and tracks, and then we arrive again at a smaller version of the big bipartite graph, and we evaluate the degree on this bipartite graph. So the degree of tracks and genres of the combined model.
The presentation. Since you are using Azure, that could have
What I find interesting is perhaps moving away from these fixed relations that we take from the data sets, and perhaps instead infer new relations between tracks and genres, perhaps because they share artists or they share, I don't know, have other common properties. So the genres that we use are similar to the talk we had before, are user tags. So it's nothing that has a known ground truth, they're just contributed by enough users. And it would be interesting to see if we can make connections between tracks that were not made by users, and how this would enrich the model. Does that answer your question?
Yeah. No, not a video. Ivan.
And now for our last work, it's going to be online. It's a work from University of Madrid in Spain, from Oscar, Andres, and Ivan. I think it's Ivan is online. And they are representing a framework for implementation in Spanish with application domain.
Sorry, I have to.
Okay.
So you should be able to share your screen, or do you want us to put the video?
I can give the presentation.
Wait.
We can hear you.
Let me share the screen. Can you hear me now?
Get back with the laptop.
Hello, can you hear me now? Better?
C'est le truc qui marche pas bien. Tac, tac, tac. Ça. So do you want to share your screen?
Yes, yes. Can you see it?
Yes. So whenever you want, you have to.
Okay. Thank you, Javier. Thank you so much. And good morning to everyone. I'm sorry for the inconveniences, the technical problems I made, and I wish I could be there with all of you. I hope you are enjoying the conference and you're staying in Samatan. Well, the work I'm going to present now was done in collaboration with my students, Andres Segura, what's happening, and Oscar Gomez. And in this work, we are going to present an argument-based search framework and an implementation and evaluation of the framework for Spanish corpus in the in-participation domain, which is a novel domain in the argument mining field. This is an outline of my presentation. I will start by introducing the motivation and goal of our work. Next, I will present the case study and the proposed framework. And finally, I will explain some outcomes and results of the work. I will conclude with some findings and future research lines. So nowadays, there is a plethora of interactive technologies and digital channels that promote the generation of textual content with rich argumentative information. For example, in social media, people express opinions and explain the reasons in favor or against such opinions. In e-commerce sites, customers provide detailed reviews about pros and cons of products. And in web forums, users discuss a variety of topics. Apart from these channels, we also have many domains and applications where electronic documents record transcriptions of argumentative discourses. For example, court orders in law, parliamentary debates in politics, and proposal and discussions in citizen participation. In all of these cases, the automatic extraction and search of arguments and the relations between these arguments can be very useful to support decision and policy-making tasks. Argument mining is a field that has around 10 years and is a field that intersects several areas like natural language processing, information retrieval and extraction, and machine and deep learning. In the field, there has been recognized three main tasks, which are shown in this picture. The first one is to detect the fragments of a text which contains some argumentative information. Then, from these fragments, we have to identify the argument components. I don't know why the slide is changing. Identify the argument components in this fragment, for example, claims and premises. And finally, the last task is to recognize the argument relations. Independently of the approach that we follow to address these tasks, in general, we use a variety of linguistic features. Here in the slide, you have some example. For example, you have features at sentence level, like, for example, the length of the sentences, the use of some linkers that express some argumentative information, the use of grammatical features, like, for example, some adjective and modal verbs, syntactic features, like some 13 patterns that express arguments, and then, of course, some semantic information. In the argument mining field, in general, there has been a focus on legal documents, essays, and news items. So there is a limited set of domains, and most of them has been addressed using corpus in English. In the IR field, in the information retrieval field, there has been a recent interest in argument search tasks, as shown in the recent edition of the Touché labs at CLEF. And in these labs, as you can see in the slide, there has been addressed a couple of specific tasks related to finding arguments for particular scenarios. In the intersection of these fields, we aim to develop and evaluate a general argument-based search framework with some novelties. First of all, we propose a new task, which is the keyword-based retrieval of documents enhanced with the structured argument information. We also propose a new argument model, which is more complex than previous model, as I will explain later. We have implemented several argument extraction methods. And as I said before, we address a new domain, which is e-participation, and focus on the Spanish language. Let's go with the case study. So the case study we address in this work is about e-participation. E-participation means the use of software technologies to support citizen participation initiatives. Here in the screen, you have an example of a platform, a typical platform of citizen participation, where citizens express some proposal for a city to solve some other some problems or issues of the city, and people also discuss. Sorry, I'm not pressing any button. And people also express discussions about the proposal. So here in the discussion, there are many comments and arguments given about the proposal and the comments themselves. So the thing is that most of the e-participation platforms nowadays are based on web forums. So you have to imagine that these forums that are shown in the slide are very large. They are difficult to follow and to get some conclusions about what are the pros and the cons given about a proposal. So in this sense, conventional web forums promote social interaction. They have some advantages. For example, they allow an easy and fast content generation because you only have to post free text. And also they promote a smooth and large-scale interaction because you can comment directly and follow the comment threads. So it's easy to interact. But they have some disadvantages. For example, they have none or very limited functionalities for content organization, filtering, and analysis. The information could be dispersed and redundant because the forums are organized by time, so they are not organized by topic or by categories. And in this structure, it's challenging to process the argumentative information beyond the discussions. So there are argument-driven tools that promote the production of reduced and collective knowledge, and we want to use some of the methods using these tools to address the traditional web forums. In particular, we are going to focus on Decide Madrid. Decide Madrid is a e-participatory budgeting platform of the City Council. It's a web platform where Madrid residents can make, discuss, and vote proposals for the city. Those proposals that obtain the higher numbers of votes and of supports can obtain funding for the implementation by the City Council. So there are many data about the proposal, and we are going to focus on the summary description and comments of the proposal because they are the textual sources where we are going to search for the arguments given by the citizens. Well, let's go with the framework. Here you have an overview of the framework. You have details of each component in the paper, but here I just want to mention that there are some modules about argument mining, the extraction of arguments, and also a tool to annotate that allows users to annotate arguments in order to implement and to test machine learning methods to extract the argumentative information. And then with all the annotation provided by the argument mining modules, we have implemented a search engine that is based on the vector split model, but enhance the results with argumentative information. So at the end, the final outcome of the framework is a set of results of documents and arguments relevant for a given query. The proposed framework has a novel argument model, which is composed of the classic premise, claim, and major claims components. But differently to previous work, we consider a number of different types and subtypes of argument relations. Here in the slide, you can see them, a taxonomy of argument relation. We have cause relation that express, for example, reasons or conditions for another argument. Clarification that introduce conclusion, exemplification, restatement, or summaries of argument, consequences, contrast, elaboration, etc. As I said, you can find all the descriptions and details about this taxonomy in the paper. Here, I'm not going to enter also in the argument mining method, but I have to say that so far we have implemented a simple syntactic pattern matching, a feature-based machine learning classification method, and also very recently we have implemented an embedding-based deep learning network to extract the argumentative information. For the information retrieval module, I have to say that the search model beyond this model, this component is based on the vector space model, and it also has a ranking strategy that modifies the document, the ranking retrieved by the information retrieval component, we taking into account the controversy of the documents. Also, you have some details about these controversy metrics and how to combine them in the paper. Outcomes and results. First of all, I have to say that we have make available, public available an annotation tool. We are implementing a new version of the tool, which will be released in the next weeks. The annotation tool allows you not only to annotate the components and relation between arguments in a given text, but also allows us to evaluate afterward possible argument extracted by computational methods. And we have used this tool to preliminarily evaluate the result given by one of the implemented methods. The outcomes of the framework are given in JSON structures. Here you have an example of a JSON object created for an argument that evidences a contrast premise on a proposal in favor of using Madrid public transport with pets. I'm not going into detail, but here you can, the framework gives you the different components of an argument, the types of the arguments, also the linker that that have been identified as in the relation of the arguments, etc. Here I show you an example of an argumentative thread obtained for a particular city proposal. You can see in the slide that there are different types of arguments given to the proposal. For example, there are some support arguments that express consequences or goals about the proposal. There are other support that express causes or reason, and there are other contrast and opposition arguments for the proposal. As a preliminary evaluation, we have considered a limited set of 80 proposals covering 10 categories and having highest controversy, and they corresponding more than 5,000 comments. In the experimental setting, 3 evaluators test the framework with 3 different queries happening in the slide, and they have to evaluate the documents and the arguments retrieved for these queries according to several metrics. In particular, we distinguish between topical relevance and rhetoric quality. As you can see in the slide, the results are acceptable, but there is much room for improvement, and we have to further work on all the implementation of the models of the framework. Well, to conclude, just to summarize, we have presented a general and flexible argument-based search framework, and we have conducted a preliminary implementation and evaluation on a dataset with citizen proposal and discussion generated in an online participatory platform. In the current implementation, we have considered various argument extraction methods, an easy-to-use tool for argument exploration, annotation, and evaluation, and the document retrieval engine, built open vector space model, and a ranking strategy that exploits certain controversy metrics. There are much more to do. We envision several open research lines. For example, we want to develop a argument-based document retrieval method, because so far we have used just array ranking technique. We want to consider alternative controversy notions, increment, of course, the size and quality of the corpus, and evaluate on other data sets and domains. Finally, we could also measure additional argument quality metrics. So this is all. Thank you so much for your attention.
So, is there any question for Ivan? Ivan, I guess that you can hear me. I don't know from
more or less.
Ivan. Okay, I guess it's here the best way to ask you. So I have a comment or just a question. Did you consider to study the annotator agreement? And I think that can be done in two sides. One on the argument annotation, like with classical measures of Cohen agreement or whatever you want to use. And also in this experiment that you just did, you study that or you plan to? Because if you want to release the data, it should be interesting to have that number.
Yeah, that's of course a very good question. And the study that we did is very preliminary. And we collaboratively annotate each of the argument of each of the comments given the proposals. We have to extend the number of comments and arguments to be annotated, and we plan to follow independent evaluation in order to measure the inter-agreement annotator between annotators. So this is something that we have to do. We wanted to do something quickly because it's very difficult to annotate arguments. You cannot imagine, it's very difficult, even for a human. So this is just a first approach that we wanted to do, and in order to obtain or to achieve a way to annotate the arguments, we have to make some minimum issues to be considered when you have to annotate, especially not only for claims and premises, which are the main components of an argument, but also the relations, because some of them are very subjective. So of course, this is something that we have to do, and we plan to release. We have published everything, the data, the annotation, the tool, but we want to extend everything, and we will publish them in the same URL. You have the address in the paper, but you can contact me, of course, or any of the authors, and we will be very happy to share everything.
So the current version of the data is already released?
Yes.
Okay. So is there any question or comment? Okay, so thank you, Ivan. We are finishing the session now.
Thank you to all.
Thank you for your talk. So I don't know, Josen is not here. Should I be here? Or...